got that there. Now I think we're ready to start. Okay. All right, let's look at the midterm exam and go through the solution set for that. And this is probably one of the more important lectures to look at because I'm giving you the answers to probably 40% of the final exam here at there. So those of you that are bored and don't want to be here, I'm sorry, but this is probably one you might want to stay awake for or get the notes from your friends out there. So, all right, the first question is determine the voltage levels. This is standard TTL levels. So when we look at this right here, and I'm going to actually cheat here a little bit. Copy and the reason I put it all in one note is so that I can write on it. That there's, as I said, I'm cheating simply because I can write my answers right here next to it on the right-hand side. That way, that there. So, and I'm recording this. So now it doesn't look like the figure copy, but we can go back and forth and look at the figures up there. So number one, this is standard TTL level right there, and you know, you go from 5 volts to about 3 volts. You know, maybe 2.7 volts, something like that right there. I'm not very picky on that level right there, but there's that range right there. About 3 to 5 volts is considered high right there. And going back up there, so this is VL low minimum, that's VL high back, that's your 5 volts. This is your 3 volts. Your low is roughly 0 to 0.7 volts right there. So VL minimum this is VL minimum right there. This is VL high right there. Those are the 3 levels, 4 levels we're looking at right there. So we go back and we look at the drawing right there, right here. We're looking here, and if you look at the drawing, I hate to say this, but the answer is right there on the drawing. If you got that one wrong, when you're looking at this, knowing that this is 5 volts right here on the top, 4 volts, 3 volts, this shows about 2 volts there. Really, it's closer to 3 volts is what I'm counting, but I don't think I'm marking my wrong for 2 volts. That there, that's showing 2 volts. This is 0 to 0.7 volts right there. So that's the range that there. So again, the key thing right there. All right, this one didn't copy, so I'm going to go ahead and just talk about this there. The frequency on this one right here is, this thing recycles at 50 nanoseconds. You can see the 50 nanoseconds right there. Right there. And it's got about a 75% duty cycle. And I'm just guessing that to be about 75%. That there. I don't have any markers to tell you that this is 75, right, or 12.5, but right there. But you can kind of guess that if this is 0, this right here is right about there is 25 nanoseconds. So this is about a 75% duty cycle. I had a number of people tell me 25%. It's the time on divided by the period. That's there. So it's off for 25%, it's on for 75%. So, and the frequency in this particular case is 1 over 50 nanoseconds. So 50 e to the negative, well, that's not doing me any good there. This calculator doesn't help me any here. Right there. For whatever reason, this calculator doesn't have the e to the x key button right there. Most of your calculators do, but 50 nanoseconds on a standard calculator, 1 over x. One of my calculators right here. I got 50 e nanoseconds is 10 to the negative 9. Equals 1 over x, and oh, mine gave me something funky right here. I don't know how to use our calculator right here. Clear. 1 over x and 50e 9 minus right there. And that's even worse. What am I doing wrong with my calculator? That's why I should carry a regular calculator instead of these phone calculators. I don't do this very often. 1 over x, 50 e 9 minus. And this isn't even a backspace key. 50 e. Well, $20 megahertz? That sounds about right. I'm going to fight with my calculator until I get the right answer anyway. Yep. All right. You said 20 megahertz? Yeah, okay. And why am I fighting with my calculator? 20 megahertz is right, and these calculators definitely out there. So let me just kind of write that down here as we go back to. So this was 20 megahertz, 75% duty cycle. All right, question 2. I'm not going to write this answer down because I don't have room. Explain the reason digital electronics uses binary as its primary numbering system. Because digital electronics uses transistors that are either only on or off. That's the only thing you need to do. It's not simpler to convert. It's not simpler that transistors are on or off, so you only have 2 states. Thus, you only have 2 symbols. You can use 1 or 0. A transistor is on or off. I saw lots of answers there, and I saw lots of wrong answers on that question. So that was one that many people got wrong right there. So the right answer is transistors are on or off. There's nothing easy to convert from. There's nothing simpler. It says digital electronics are using transistors that are on or off right there. So same thing as if you're doing signals, you either have a 1 or a 0, 1 or a 0. You don't have 3 states, you don't have 4 states, you have 1 or 0, on or off. That there. What's that? Which ones? On 2A? 2A, the right answer is that transistors only have 2 states, on or off. That's the right answer. So if you had something else to say that's easy to convert from this numbering system or something like that, that's the wrong answer. The right answer is transistors can only be on or off. Right there. You only have 2 states. Right there. So, that there. So, same thing as when you're doing digital communications, it's a 1 or a 0, on or off. And therefore, we only have one finger, 0, 1, 0, 1. So, therefore, we're stuck to binary numbers is what we're stuck with. It's the physical result of what the electronics gives us. It's 1 or 0 right there. We don't have 10 symbols like we have 10 fingers. We have 1 or 0. They're on or off. So every other answer you have is wrong right there. Right there. So, and the reason I put these questions here is it's better for you to get them wrong when this is worth 10% of your grade than when it's worth 60% of your grade. So if you got the wrong answer, don't get upset. Just realize that you want the right answer in 4 weeks' time, right there. That's what you want to keep in mind here, is that these questions are here for a reason, is that I don't want you to get it wrong on the next time you see it. And you will see something like that. Convert the following digital numbers, signed decimal numbers, to binary. All right. These are, they're 110. You could use the calculator for this. That's perfectly fine. most people did it by hand. It doesn't really matter whether you did it by hand. You know, if you did it by hand, you would start off here. You've got 8 bits, and your numbers are 1, 2, 8, 64, 32, 16, 8, 4, 2, 1. That there 10. You're going to have a 1 there. You take 110, subtract 64. What have you got left there? You know, I'm going to pull up the calculator. Well, I'll pull up this one here. I seem to do better with this one today. So what am I doing here? So 110 minus 64, I'm left with 46. So I got a 1 here. So I'll subtract 32. I got 14. I have a 0 here. So 14. I have an 8. So minus 8. I have 6 left. So I have a 1 here, a 1 here. So the right answer is going to be 0, 1, 1. 0, 1, 1, 1, 0 is what this should be the right answer there. The next one is negative 95. And the negative 95, basically you have to start off with converting 95 and then finding the 2's complement. It's a 2-step process. So 95 going through, and I'm just going to change this to a green color right here. 95, you got 0, 1, 95, subtract 64. I got 31, so a 0, a 1, minus 16. I got 15 left, which is going to be 1, 1, 1, 1. So my number is 0, 1, 0, 1, 1, 1, 1, 1. We find the 2's complement of that, and that's going to be 0, 0, 0, 0, 0, 1, 0, 1. We add a 1, 1, 0, 1, 0, 1, or 0, 0, 0. This is the right answer right there. Right. That is the right answer that you would get there. And if I use the Windows calculator right there, which may or may not work for this right here, convert that to programmer. We put this to byte in order to get that to work right. And we say that it's 95 plus minus. And there's our 1010001 right there. So that's the process right there. C is a tricky one. Right there. C is, if processors were designed to have 6, 12, 24, 40 bits instead of 8, 16, 32, 64, we probably wouldn't use hexadecimal for representing these binary numbers. Explaining how a numbering system based on 3 bits instead of 4 bits as used in hexadecimal would work. Well, actually, what I'm saying at that particular point is the question is requiring you to think a little bit right there. And when we look at C, I'm not going to necessarily write this answer down, but when we look at C, what we're looking for is we're going to use something that's called octal right there. It's going to be based on 3 bits, so it's going to have numberings between 0 and 7 right there. So we would use base 8 instead. That's the key that we're looking for, is we will use base 8 instead of base 16 in order to have our shorthand numbers. So we would write numbers that would be 3, 2, 6, base 8, which would go into binary as 0, 1, 1, 0, 1, 0, 1, 1, 0, for like that right there. We would group them in groups of 3 instead of groups of 4. And we would use a numbering system based on 8 numbers instead of, or 8 levels instead of 16 levels. Hex is based on 4 bits, and we got 16 levels. 4 bits gives us 16 levels, so it's base 16 or hexadecimal. Here we're saying we're going to use base 8, which is based on 3 bits, right there. So what I'm trying to get out of you is the fact that you would now have a numbering system that would be based on 3, that will be based on 8 instead of based on 16. We use hexadecimal because we break it down into groups of 4 because our standard words are, the first microprocessor had 4 bits. The first standard microprocessor that's been used for a long time, including the one we're using, has 8 bits. The next generation has 16 bits. The next generation after that is 32 bits. And now most of the top microprocessors are 32-bit or 64-bit processors. So we use base 16. Now I'm saying, well, let's say Intel didn't use 8. Let's say they used 6 bits instead. Right there. So that's what I'm looking for on part C, is that, why are we using base 16? And the reason is because we've got groups of 4. So now all of a sudden the rules change, we got groups of 3. What would we use instead? And here, the biggest hint is that I gave you this 3 circle right there, based on 3 bits right there. So it would be based, octal is based on, hexadecimal is based on 4 bits. Now we're basing on 3. So we would use octal is what it's called. And incidentally, it is a numbering system that has been used with microprocessors. A company a number of years back called Digital Equipment Corporation, or DEC, put out a number of mini computers called the VAX and the VT1. VT100 was the terminal, but the VT103, I can't remember what the other one is. They had another one out there that was fairly popular back in the 1980s. DEC has gone away, and their microprocessors were actually based on 27 bits. So they used a group of 9 octal digits when you represented them in binary, or that there. So, okay. Convert the following sign to hexadecimal right there. And I think I can give myself some room here let's just give myself a little bit of room here. That there. This right here is actually going to be, if it's you can do this multiple ways. You could write this as 15 and add that to that there, or you can do it digit by digit. I probably would just simply say that this is 4F hex, so that's 4 times 16 plus 15 right there. You can do it that way, or you can go through one bit at a time, or you can just use a calculator. I get that if I use that right there, and I did allow you to use calculators, and on the final exam you'll be allowed to use calculators right there. Right there, what was that number that we had right there? Oh, I lost my notepad right there. That was zero. So in binary, that would be 0, 1, like 0, 0, 1, 1, 1, 1, and that comes up to 4F or decimal 79 right there. So that's the right answer, 79. The other one was a little trickier, and that one was that there. This one here is it's a negative number, so you have to find the 2's complement for that, and the 2's complement of that is going to be 1, 1, 1, 0, 0, 1, 0, 1. So it's going to be 0, 1, 0, 1, 1, 0, 0, 0, add a 1, and I've got 1, 1, 0, 1, 1 right there. Right there, so that looks like it's 16 plus that there, or I can use the calculator for that there. One and okay, number 1, 1, 0, 1, 1. 1, 1, 0, 1, 1, and I get negative 27 is what I get there. If I put the original number in, the original number was that there. Negative 27. So I get the same thing if I put it in the Windows calculator right there. Negative 27. So that's what we would get right there. So you can do that either way right there. Right there. So that there. Follow the binary. Those should be very, very quick and easy. Right there. That's going to be 0011, 0010, right there. Right there. I just put the leading zero there. You don't necessarily need the zero. Oh, right there. I guess these are 4-digit numbers. So I guess I do need to write 000, 0010, and then the last one is F, right there. You can do that by inspection. The next one is 111, 0101, 0101, right there. That's only 3 digits right there. So I'm just converting and that first one should have 4 ones in there. All right, there should be groups of 4. So it should be F55 is there. And remember, going from hexadecimal to binary is very, very quick right there. Convert the number 45. Almost everyone got that one right, actually. Right there. Almost everyone got that one right. That is simply going to be it's going to be 4 times 7 plus 5, and that looks like it's 32, right? Well, actually, this says it's 33. It calculated it for me. That was interesting. But is that right? 4 times 7, yeah. That's it. Is that 33 is right? Yeah. Well, I just kind of shocked that it calculated it for me real fast right there. As soon as I hit the space bar, the 33 popped up, so I didn't expect OneNote to do that calculation. That's why I got confused. All right. That was question 2. Question 3, give the truth table. I'm not going to go through all those that there. You should know the OR gate looks like that, the AND gate looks like this, and you should know the truth table that there. Just expect to see that on that there. And I think 99.9%, I don't think anybody missed that there. Draw the logic expression for that one. That one is fairly straightforward. We have an AND gate with A, B, C. I put the bubble there. And then I have a NAND gate right here with A and C, and that all goes to an OR gate right there. So that one's fairly straightforward. Give the truth table for part B. That there, I guess I should go through that one because that one is fairly straightforward. The way that you would want to do that is you would want to write this A, B, C right here. And then we would have A, B naught, C. We write that one there. And then we would have A, C naught right there. Now we could put another table in here and put this knot on that here if we want to. And then our result is everything, those two ORed together. We're going to OR this one together with this one right here. This one's just to help us write that one. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Right there. And my lines are far from straight. Right there. So A, B naught, C, the only place that's true is right here. Every place else, that's all going to be 0 right there. Right there. That one's fairly straightforward. AC would be true here and here. Right there. So A not C is going to be true here, 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 right there. As it turns out, this one here is that our truth table is going to look like this right here. This is going to be a 0 here. This is going to be a 1, 1, 1, and a 0 right there. It's going to look something like that right there. For some reason, yeah, that's right. That's what you would get right there. Most people got that right. A few people had a 1 here. Right there. So that one was fairly straightforward right there. Okay. Now I'm going to cheat a little bit here. These are where the problems get a little bit longer right here. Let me just copy this right here. Actually, I'm going to copy everything here. Copy. I just want to put it on the next page right here. Right there, so we've got some room to work. Draw a product of sums directly from the circuit. Do not simplify. This one's fairly straightforward. I just write the equation right there from this table right there. Every place there's a 1. So there's a 1 here, there's a 1 here, there's a 1 here. So I have 3 places where there's a 1. So it's going to be X out is equal to A naught, B, C, D naught, or A, B naught, C, D, or A, B, C naught, D naught, right there. So that's really all you need to do for that one. It's straightforward, right there. Next one, refer to truth table 2 using the K-map developed the simplest Boolean expression for the product of sums. This is the tricky one right there. This is the tricky one because this is the one where I have to read the zeros out. And I think a number of you forgot that there. Because sum of products is what we just had right there. This is the sum of products notation right there. Right, this is product of sums. Draw the product of sums. I just did this one wrong too. That's the product of sums. I actually did this one wrong too. I just misread that. I just did the same thing you guys did. So I probably gave you all credit for this problem, and I shouldn't have. I need to go back and lower everyone's grade. Actually, I'm not going to go back and lower your grades. I'm not there, to be honest, but I just did this problem wrong. I just misread the problem, and I know that a number of you misread it too. So actually, the reason I say that, actually, let me stop. Actually, let me just go ahead and do that. X out is equal to this right here. Right there. That is true, but what I want to do then is I want to go through and I have to convert that over. Is what I have to do right there. Actually, to do this one right, we have to read out the zeros. So this one is actually a very nasty problem. I'm going to start it. I'm not going to finish it. I won't I better make sure I didn't put this one on the final exam worded this way. And what makes it nasty is because I've got 12 terms. So if you see this on the final exam, start it, go back and finish the rest of the exam and come back. Show me that you know how to work the problem, and then we'll get there. So this answer is wrong. That answer is wrong. We will start with saying X naught is equal to A naught plus B naught plus C naught plus D naught times, we have to do this right, A naught, B naught, C naught, D naught plus A naught, B naught, C naught, D plus A naught, B naught, CD, or C, D naught, or A naught, B naught, C, D. I'm there. Next one is A naught, B, C naught, D naught, or next one is A naught, B, C, D naught, or as you can see, it's getting really nasty really fast. This is not the problem I intended to put on there. A naught, B, C, D naught, or no, that one's not there. That's there. This one here should be A naught. That should be on this one right here. A, B, C naught right there. Okay. Plus we skip this one here because it's a 1. A, B naught, C naught, D naught, or going on to the next one. Right there. A, B naught, C naught, D naught, or right here, our next one is A, B naught, C naught, D, or A, B naught, C, D naught. That's this one right here. We skip these two, and then we have the last two. A, B, C naught, D, or, and the last one is A, B, C, D. So that's our function right there. There should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I got 13 right there, yeah. 13 is right because there's 16 right there. There's 13 terms. It's a nasty problem right there. Hopefully I didn't give you anything that nasty. I don't intend to give you anything that nasty, but sometimes they accidentally show up right there. If you see something that nasty with me, it was right there. What you need to do at this point is you need to then realize what the function is right here. And I'm just going to say dot, 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 because at this point, I would say just show me that you know how to work that, and that is equal to then A plus B plus C plus D, A plus B plus C plus D naught, right there, dot, dot, dot. And I would stop at that point right there. So keep that in mind, that is not the complete answer. The complete answer, you would go ahead and do that for all 13 terms, but if you're on the final exam and you get something that looks this nasty, show me that you know how to work the problem. If you run out of time, you might lose 1 or 2 points. You won't lose a whole lot. Right? If you leave it blank, or you leave another problem blank, you lose a lot of points. A little bit of a warning on my final exams that there is that you're much better off answering every problem to the point that you can show me that you've got it, you know how to do it, then go back and finish the easier ones. But if you run out of time and you got a nasty thing like this and you don't finish it, if you leave it blank, you lose all 6 points or whatever I had marked on this thing here. But there, I have 5 points, you lose all 5 points. If you stop at that point, you might lose 1 point. If you leave it blank, you lose 5 right there. So always start the problem and show that you know which direction to go right there. So at this point, I would see that you know how to answer the problem right there. So I would consider that a good answer. And then you would go through and complete that for all 13 of those nasty looking terms right there. That was not meant to be right there. The next one's the same thing. Only difference is this one is actually simpler right there. Because actually, I meant to have this one say product, sum of products right there. And this one here says product of sums. This is the one that's supposed to be answered that way. And if you notice, there's far fewer zeros right there. So you would go through and you would answer this right here. X naught is equal to A naught, B naught. Well, actually, first thing you would do here is you would go through and you do the K-mapping first. This one I right there, directly from the truth table. Do not simplify using K-map. Right there. Draw the circuit right there. This one here was meant to be the sum of products. Right there. That was just a bad problem right there. Hopefully, if I did something like that, I'm going to double check the final. I don't think they've gone in for printing yet. I want to make sure I didn't do that to you on the final exam. That's it. But this one here, I say go ahead and do the K-map first. Right here. If you do the K-map first, right here, we get 1, 0, 0, 1. And I'm going to write here 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, right there. Go ahead and fill in the K-map right there and go through here. So 1, 0, 1, 1. Down here to 8 is 0, 0, 1, 1. Right there. And then finally here we're at B, which is right here. No, that's BC. C, which is 1, 0, 0, 0 right there. So in this particular case, we're going to read the zeros out right there. So we're going to read the zeros out right there. We read the zeros out. We've got one group here, we got one group here, and we got one group here. Right there. And so our function is not X naught is equal to, this line right here is A, B, A, B naught, A naught, B naught, A, B naught. Right there, is that right? Nope. This is, now I'm not, this should be A dot, B naught, A naught, B, A, B, A, B naught, right there. There. But there's C naught, D naught, C naught, D, C, D, C, D naught, right there. That looks right. Okay. So this line here is A dot B plus, this looks like A naught, B naught. You're not, that the B changes. That's A, C, D naught, or A, B naught, C naught, D naught right there. That looks like our function right there. So then we would say X is equal to A naught B with a naught across it times A naught C D naught with a naught, A B naught C naught D naught with a naught across it equals A plus B naught, A plus C naught plus D, A naught plus B plus C plus D, right there. And our circuit is going to look like this. Here's our OR gates. A, B, A, C naught, D, and A, B, C, D. D. There's my bubble, there's my bubble, there's my bubble, there's my bubble, there's my bubble. Be sure you put the bubbles on both ends right there. So that would be your circuit there using only NOR gates right there. So, that there. So obviously you can see that this here covers everything there is to cover on combinational logic. Now we've got the sequential logic, which is not part of this test. So we have other material that's not part of this test. This class is about 40%, about 60% combinational logic, about 40% sequential logic. We've covered a lot of the sequential logic. That there, I've got that there. So this is about 40% of what's going to be on the final exam. It's right here. So that there. So I apologize tremendously for this question there. That you should be able to answer. There's nothing wrong with the question. It's just that it's a nasty, long answer. It would take you probably 15 minutes to answer that completely. And given the number of questions on the final exam, if I put that on the final exam, do not finish the question. Start it and leave it go. Just use common sense. If you see a question that's going to take you 30 minutes to answer, get it started, show that you know how to answer it, and then move on. Come back and finish it. One of the things that gets very interesting is we'll look at final exams that they're, in an ideal world, time should be a factor, but it is. Time is always a factor on the final exam. And my goal as the instructor of the class, who's going to grade the final exam, is to see what you know. Whether or not you can work extremely fast is quite often secondary on whether or not I understand that you know how to work the problem. So if you see a problem like this on the final exam, start the problem, get to the point where I see you're going in the right direction that you would be able to answer it. See, if I stop right here and I show ... that tells me that you know how to answer the problem. You're going to run out of time. So then you go ahead and show the start of the circuit there. You got to remember, you got to show the start of the circuit. I just messed up. If I put this on there, then all I can say is start the problem and leave it unfinished. That will hurt you far less than if you try to finish that problem and spend 30 minutes on one problem that's worth 5 points out of 100. Don't do that to yourself. Don't do that to yourself. You look at the problem, it's worth 5 points, I get it started, I'll get 4 points out of 5 if I see that I'm going the right way. If I've got time at the end, I come back and finish it. So, that's it. But that's essentially that was the midterm. It kind of shows you what type of questions you're going to see, though. Between now and the end of the semester, I will give you, not as a midterm exam, but as kind of a take-home study sheet, examples of the other half of the class. So you're going to see probably 3 or 4 problems thrown at you that are going to look very similar to the other 2.5 questions right there. This is about half the length of what the final is going to be. So those of you that ran out of time on this, realize that you will definitely run out of time on the final exam. Because this is about half as long as what the final exam would be. The only problem is I gave you this nasty thing that they're there. I don't want that to be. Oh, okay, it's almost done. But there, I don't want you to get hung up and spend all your time on one problem. Because these marks, to be honest with you, where it says 5 marks there, that 5 marks is what I would have on the final exam. They're not the marks for this class. If you look at these questions, they don't add up to 100 marks. I left the marks as I copied the questions from the previous final exams there, and I changed the wordings or whatever. But I left the marks there to kind of give you an idea how much that question would be worth on the final exam. I will put up Probably Monday, because like I said, I'm heading to Bali tomorrow. We don't have class on Thursday. The lab is open for you to do the lab, finish the lab from last week. Just check out the board from the technician. They're just, let them know that you didn't finish it. And then I'm not there, but we've got the room, so you go ahead and do the lab last week. And then next week, what I will probably do is I should pass things back. I got them graded, but they're sitting in my office at home. There I have a second office at home where I do a lot of the grading. But I will post these questions, but not with the answers. I will post this video. So those who, I noticed that I can't remember her name. She's out here today, but she sent me an email asking me if the class was. I think she sent me an email thinking that she was hoping I would say no, there's no class because she sent the question saying, "Is there class today?" and then doesn't show up. That kind of tells me that she hadn't planned on showing up anyway. Which is kind of an interesting thing. Someone does that. I don't. But I will post this video hopefully tonight. I'll get this video up so you have time to kind of review it. If I be honest with you, if I don't post the questions, actually, you know what? Do I have Wi-Fi in this room here? No, we're setting. If I've got Wi-Fi, I can post the questions right now. Here we go. Let me see if I can connect that there. This thing's still encoding. There. I'm going to stop the video recording right there. Yeah.